Again, class. So it's Sir Gerald again. So for this part of the lecture, this is the continuation of the structure of an atom and quantum numbers. So in here, we will be talking about the distribution of electrons in an atom. This is actually what we call the atomic quantum numbers. So in here, we will be in this video, we'll be tackling the Schrodinger wave equations. Don't get me threatened by that. It's just numbers. And the last part of the lecture we will be talking about electron configuration, uh, valence electron shell, and lastly the number of electrons in the valence shell or number of valence electron. Okay, so by distribution of electrons in an atom, we will be talking more of continuation of the energy states that we have talked about or we have discussed under our video in atomic spectra. Okay, so this is just a continuation of the prior video. So by distribution of an atom, we will be using the Schrodinger wave equation, wherein the Schrodinger wave equation is actually developed by Schrodinger in 1926. He wrote an equation that described both the particle and the wave nature of electrons, wherein in some way, if you are familiar with GPS, he provided some sort of way that we can locate electrons uh, using numbers, much like how GPS works, where we have the latitude, the longitude, and the elevation or the altitude. Schrodinger wave equation works like that in some sort of way. Okay, so Schrodinger's wave function is describes the energy of electron with a given Schrodinger number, and this can be used in describing the probability of finding an electron in a volume in space. By volume of space, last time when we have talked about atoms, we have described atoms as entity wherein the center of the entity contains the neutron and the protons, or what we call the nucleus of an atom, and most of its volume, or 99% of its volume, is actually occupied by the electrons. In some way, Schrodinger wave equation describes that volume or that space that is occupied by the electrons. So Schrodinger equation can only be solved exactly by hydrogen atom. But it approximates the solution of multi-electron systems. By multi-electron systems, these are atoms having more than one electrons like hydrogen, lithium, boron, and so on and so forth. Okay, so using Schrodinger wave equation, we actually have four numbers which we call the quantum numbers. We have there the n, the l, the m sub l, and the ms, wherein n is the principal quantum number, and in N, this actually describes what we call the energy level that we have talked about earlier in atomic spectra. So this is just integers counting from 1 uh, and so on and so forth. But for now, the discovered elements or discovered atoms, we have as much as 6 or seventh energy level. So we only have seven principal quantum number. So By quantum numbers, these only describe the distance of the electron from the nucleus, meaning 1 or the first quantum number is the nearest to the nucleus, and for this notion, 4 is the furthest. And so this is the simplification of that principal quantum number. So we have here 1s, 2s, and 3s, and in which for 1s that describes the distance of the volume that is occupied by nucleus or by electrons in the first energy level. For 2s, we have here the volume mostly occupied by electrons in the second energy level. And for the third energy level, we have here the 3s. So, in that, we also have n, which is equal to 1. We have n is equal to 2 and n is equal to 3. Okay? So, in that, there is a notion or an approximation called the orbital, wherein by orbital, this is a region of space where electron is likely to be found, which is of 90% probability. Much like how solar systems and galaxies work, there is a center nucleus. For example, in the solar system, we have the sun, and orbiting or revolving around the suns around the sun is the planets, wherein we can say that the planets work as our electrons. Okay? So for the solar system, it provides the approximation that there is uh, inhabitants there, inhabitant electrons. So there is 90% of the electron density found in 1s orbital, wherein we have their greater probability that is higher nearer the nucleus. So as we go further from the nucleus, the probability of finding an electron is is going down. So the next quantum number is the L, whereas it is the angular momentum quantum number. So by angular momentum quantum number, this just give us for a given value of n, there is 0 to n minus 1 number of angular momentum quantum number. So, for example, for the first energy level, there is an angular momentum of 0, meaning to say there is only one space or one angular momentum, which is characterized by 0. Okay. And for second energy level, there are two angular momentum quantum numbers we have there, 0 or 1. Meaning to say, for electrons in the second energy level, or say 2, it may be located in the angular momentum 0 or 1, either of that. So for energy level 3, there are three angular momentum quantum numbers. It can be 0, 1, or 2. So this is not a count or kumbaga sa Tagalog, hindi ito bilang. When we talk about angular quantum number, this is a location. Okay? So for first energy level, there is location 0. For second energy level, there is location 0 and 1 or 1. For third energy level, there is 0, there is 1 or 2. So that follows that for certain angular momentum, by angular momentum, this is just a location or a space. So if we have zero location, that is the s orbital, yung pinakita natin kanina. We also have for L is equal to 1, that we have there the p orbital. And for L, which is equal to 2, we have there d orbital. Meaning to say, for principal quantum number 1, there is only the s orbital. For the second, or the principal quantum number 2, which is 0 and 1, we have their s and p orbitals. And for principal quantum number 3, we have their uh, an s orbital, a p orbital, and a d orbital. So meaning to say, 1, and 2 are locations, wherein those locations are called s orbital for 0, p orbital for 1, and d orbital for 2. So for 3, L is equal to 3, we have there the f orbital. So meaning to say, that is for fourth energy level. Okay? So in hindsight, angular momentum quantum number L is actually the shape of the volume of the space that the electron occupies. So ano ba ang magiging itsura ng volume of space na yan? Or what is the appearance of the shape of the volume of space that electron occupies? So for the sublevels L, or the azimuthal quantum number, sublevels of main energy are the locations where electrons probably move. Both principal energy level and type of sublevels are specified, describing the location of the electron. So for the first energy level, since there are no other orbitals there, we have there the 1s. Okay? So for the second principal quantum number, which is 2, we have there two orbitals. So we have, remember, the 0 and 1. So we have there 2s and 2p. Okay. For the third energy level, since we have there the 0, 1, and 2, meaning to say we have s orbital, 3s, p orbital, 3p, and d orbital, which is 3d. And the list continues. So if we have, for this scenario, if we have n is equal to 4, meaning to say our L may be 0, 1, 2, and 3. Meaning to say we have s orbital, p orbital, d orbital, and f orbital. In that scenario, we will have 4s, we will have 4p, we will have 4d, and 4f. It will continue, but as of now, I think there is no more after f. I'm not mistaken. So we have here the spectral line. You have there the S, which stands for sharp. P is principal. D is diffuse. And F is fundamental. So here are the maximum number of electrons for each energy level. So since sorry, buong mag-sync na natin. Okay, but anyway, so for first energy level, we have a maximum of 2 electrons. We will discuss later on why there are two maximum number of electrons of 2. We have here the sub levels of subshells, which is S, and we have here the maximum number of electrons per subshell, which is 2. We have here the energy level, second energy level, which have maximum number of electrons, which is 8. I don't know kung bakit nandito siya ngayon. Tuloy-tuloy na natin. 18 for third. Uh, 32 for fourth. And we have 50 for fifth energy level. Okay. Okay. So going back to the space or the shape of the quantum numbers. So if we have here the s orbitals, this look like spheres. If we have p orbitals, it look like spheres that are somehow linked to each other. It looks like an eight. If we look into that as an 2D shape, and this is d orbitals. We have five types of d orbital. We have three types of p orbitals. And for the F, for now, there is no, let's say, there is no model to present the F orbitals. So, ito na lang muna. So, for the next part or the next quantum number, we have the M sub L. So, for the M sub L, actually, this is what we call the magnetic quantum number. So, this only describes the inclination or the what we call the alignment of the quantum numbers. So or the L quantum numbers. So for any given value of L, we only have this range. So for one or the p orbital, there can be negative 1, 0, or 1 ml or m sub L. For the second or the second L or the d orbital, we have there negative 2, negative 1, 0, 1, or 2. And for that, magnetic quantum numbers just entails or talk about the orientation of the orbital in space. So, what is presented by that? Ibig lang sabihin yan, kapag meron tayong p orbital, meron tayong tatlong orientation sa space. So this is for L, which is equal to 1. This is the orientation in space. So for negative 1, we have here both of the nodes or both of the circles or the spheres are aligned with the x-axis. For the 0, we have here both of the spheres are located along the y-axis. And for the 1, we have uh, spheres that is aligned with the z-axis. So, how about S? Since S or L, which is equal to 0, is just 0, its M sub L is just equal to 0, meaning to say, it only have one orientation. So if we are to look into that using the 3D space, it is located at the origin or its center is located at the origin. So there is no such thing as orientation. For any orientation, it will look the same. So for d orbital, we have five orientation in space. So we have here that we have here a space that is located in x and y. We have here a space that is only located in z for the both orbitals, and we have here uh, located in xy or in the middle of x and y, not along the axis. Also, we have here xz, which is located in the plane of X and Z, but not on the axis. By not on the axis, hindi mismo ron sa arrow. And also we have here the one located in YZ, okay? Or in the planes of YZ, not on the Y and Z axis itself. Okay. So for the last part or the last quantum number, we have the M sub S. M sub S is what we call the spin quantum number. So by spin, this only entails the direction of the spin of a certain electron. It can be positive one half or negative one half. So this entails only the direction of the spin depending on the much like our magnets. So in that, if the spin is positive, it is clockwise, and if it's negative, it is counterclockwise. This is just the way that they detected the positive and the negative spin of electrons. So for the quantum numbers, this is the summary. We have the existence or the energy of electron in an atom is described in its unique wave function. So, using Pauli exclusion principle, no two electrons in an atom can have the same four quantum numbers. Meaning to say, if we have carbon that have six, six electrons, all of those electrons have different quantum numbers. Okay, so it is much like how seating arrangement works. For this example, in an arena, each seat is uniquely described. Let's say we have E row 12, seat 8. So yeah, so each seat can hold only one individual at a time, much like how electrons work. For each quantum number, there is only one electron in that quantum number. So, in that notion, we have here the table that's contains the relation between the quantum numbers and the atomic orbitals. So, if we are to add the spin. So for any orbital, there is actually two seats or what we call two spaces. So for one is there is one is that has a spin of positive one half, and one is that is with the spin of negative one half. Eh? Negative one half. Sorry. Okay, so in that, each atomic orbital contains two electrons. So two electrons for 1s, two electrons for 2s, two for 2p, x, 2py, and so on and so forth. Okay, so quantum numbers. So this is just the summary of that. So we have there the shell. We have here the subshell, which is electrons with the same values of n and l. We have here the orbital, which contains the magnetic spin. Magnetic. Yeah. And so, in that, how many electrons can an orbital hold? Sagot ko na to kanina. If n and l and ml is fixed, and we have magnetic spin, which is one half and negative one half, meaning to say, for every wave equation, there is positive one half or there can be a negative 1/2, meaning to say uh, an orbital can hold two electrons. So how many 2p orbitals are there in an atom? So for 2p, if we have n which is equal to 2, we have L which is equal to 1, meaning to say there are ml or m sub L that is negative 1, 0, and positive 1, meaning to say we have three orbitals. These are the three orbitals. So how many electrons can be placed in 3D subshell? So in here, the first thing you need to do is I first identify the energy level, and for that is obvious. So we have there three, okay, and then identify the L. Since this is D is L is equal to 2. Okay, so if we have L is equal to 2, then ML is, or M sub L is equal to negative 2. Negative 1, 0, plus 1, or plus 2. So we have 5 orbitals. And as we have stated earlier, each orbital can hold 2 electrons, meaning to say we have 10 electrons. Okay? So this is just the illustration of energy orbital in a single electron atom. This is just the jumps. So energy only depends on principal quantum number n, since we only have one electron. Meaning to say that one electron may be located here with a spin of positive, or it may be here with a spin of negative. So it depends. But it only depends on the principal quantum number. But when we talk about multi-atom or multi-electron atoms, we will have here a different sense of how we look into that. So we have here the energy orbitals of multi-electron atoms. So energy depends on uh, the principal quantum number and the L. Okay, so we have here n, which is principal is equal to 1 and L is equal to 0. So for uh, n is equal to 2, we can have two more energy levels. So we have here n is equal to 2 and L is equal to 0. If since we have 2 as an n, and our L can be 0 or 1. So we have another energy level which is n is equal to 2 and L is equal to 1. That also works for the third energy level. If we have third energy level, that can be n is equal to 3 and L is equal to 0. N is equal to 3 and L is equal to 1. Also, we have n is equal to 3 and L is equal to 2. Okay? So, in filling up electrons in the in such a way, if we are to talk about stable atoms, we need to fill up electrons in the lowest energy first, since lower energy tends to go into chaos. So, in hindsight, kumbaga, kung meron kang isang bahay, at sa isang bahay nagkaroon ng party, at maraming batang pumunta, at lahat ng batang yun ay punong-puno ng energy, magulo yung party. I mean, maingay, makulit, masaya. But once that napagod na lahat ng mga bata or nasa lowest energy level sila, tahimik. So, that also works here in our energy levels when we are to talk about electrons. we first need to fill up the electrons in the lowest energy orbitals using the off-bulk principle, wherein if we have hydrogen in its most stable state, or what we call ground state, here is how we fill up the electron. So for the next part, we have hydrogen. That is hydrogen. So we have here 1s1. 1 being the principal energy level, S being the orbital, and 1 being the number of electrons in that orbital. Okay? For the next part, it's the next atom is helium. If we have helium, helium has 2 electrons. So if we are to fill up this energy level, we will write that as that. So for helium, we have 2 electrons that are located in the first energy level and in s orbital, or L is equal to 0, wherein the first electron is moving positively and then the second electron is moving negatively. Okay? So ganyan natin siya fill up and down. Okay. So what's the next? Lithium. Lithium. Lithium has 3 electrons. Okay, so we just write that as that. So we have lithium atom at ground state has 2 electrons in the first s orbital and 1 electron in the second s orbital. So tuloy-tuloy lang natin, beryllium, 4 electrons, ganyan siya. So we have 1s2, 2s2, or 2 electrons in the first s orbital and 2 electrons in the second s orbital. Okay, we have boron, 5 electrons, like this. And we have here 1s2, 2s2, and 2p1. How about the next? Carbon. We have carbon has 6 electrons. Did we write? Ganito ba natin siya isusulat? No. Ganito. Bakit? Kasi papasok na dito yung tinatawag natin isa pang rule. Wherein, when we talk about or filling up electrons in orbitals that have different subshells or different orbitals or different spins, the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spin. Meaning to say, if we have here our p orbital, we first need to fill up all of the 3 orbitals before we fill up the negative spins. So meaning to say, if we have carbon which has 6 electrons, we will fill that up this way. Okay. So meaning to but we can still write that as this. So we have here 1s2, 2s2, 2p2. We can break down the p orbitals, but for convention, we just write this way. For the next atom, we have nitrogen, which has 7 electrons. So we just write that as this. Okay, continuing. For oxygen, and for fluorine, and for neon. So, as you may have noticed here, if we continue on filling up the subshells, we may notice that we have here 3s. And the next energy level is 3p. But the next energy level is 4s. We have skipped 3d. Why is that? So, in hindsight, when we talk about energy levels, we need, as stated earlier, we need to consider the N and the L. And in that, we may look into that as our basis for the energy level. In that, we just need actually to add the N and the L to identify which energy level or which orbital has the lower energy. So, for example, we are to compare 3D with 4S. Why do we need to compare that? Just to see which which of the two comes first in the energy levels. So we have here 3D, which is has then an n of equal to 3, and 4S with n that is equal to 2. D is has an L value of 2, and S has a value of 0. So if you are to add that, 3 plus 2 is actually 5, and 4 plus 0 is 4. Meaning to say, 4S is lower than 3D when we talk about energy levels. So using that, 4S has lower energy than 3D. So if we are to talk about 3D, which is N is equal to 3, and 4S, which is N is equal to 4, the L of 3P is 1, and the L of S is 0. Meaning to say, if we are to add those N and L's, we have 4 and 4, so 3P and 4S has the same energy. But for the sake of the number, we write 4S, or we fill up 4S right after we fill up 3P. Okay? That is why we have this order of orbitals for filling multi-electron atoms. Alright, so just like this, if we are to compare 5s and 4d, okay, again, for 4s, n is equal to 5, l is equal to 0, and for 4d, we have here n is equal to 4, and d is equal to 2. Eh, no, not d, l is equal to 2, okay? So if we are to add that, 5 plus 0 is equal to 5, and we have here 4 plus 2 is equal to 6. Meaning to say, 5s is lower than 4d. That's why we need to fill up 5s first before we fill up 4d. Okay? And that's also true for 6s and 4f, since f has an L of which 3. So that's how it works. Okay? Other examples. Let's say we have, why do we need to fill up 5p first before 4f? So we have 5p. N is 5. L is 1. We have 4f, so which is has an N of 4 and an L of 3. Okay? So this is, if we are to add that, this will be 6 and this will be 7. Meaning to say, 5p has lower energy level than 4f. Okay? In that, we have this shortcut. So we have 1s, 2s, 2p, 3p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and 6s. So if you are not so good memorization, just like me, you can use the principle of N plus L to identify which energy level is lower than the other. Okay. So in that, we are moving into what we call the electron configuration. This is just somehow the summary of all we have discussed from this moment on regarding quantum numbers. So if we are to describe electron configuration is how the electrons are distributed among the various atomic orbitals in an atom. Let's just add some words here. An atom in their ground state, meaning to say atoms that are not in their excited state. So for example, we have here 1s1. 1s1 meaning to say we have here one electron in the first orbital in the first energy level. So we have here the principal quantum number, which is 1. We have here the S, which is the angular momentum quantum number L, and the 1, which is the number of electrons in the orbital or the subshell. Okay, so in that, we have there the orbital diagram of hydrogen. So we have there the 1s1. Okay, so that is true for any other electron configuration. So let's say we have here magnesium. Magnesium has 12 electrons in their ground state. Okay. So using this, we have here 1s2, s2, p3, p3s, 3p, 4s. So we have here 1s2, 2s2, 2p6, 3s2. And if you are to add that, we have here 2 plus 2, which is 4, plus 6, that is 10, plus 2, we have here 12. Okay? Or we can abbreviate that as neon 3s2, wherein we use the noble gases to identify the electron configuration of some other electrons. Okay? Wherein in here, neon is 1s2, 2s2, 2p6. Okay, what are the possible quantum numbers for the last or the outermost electrons of chlorine? So chlorine has 17 electrons, okay? Meaning to say, if we are to use our arrangement again, we will have 1 S2, 2 S 2, 2p6, 3 S2, 3 P5. Meaning to say, we have here 17 electrons. And the last electrons added up to 3p orbital. Nandito sila. So, meaning to say, there can be, we have an energy level which is 3 for the outermost electron in chlorine. We have an L which is 1 because of the p orbital. And the spins may be, or the locations may be -1, 0, or +1. And there can be a spin of +1/2 or -1/2. Those are the possible quantum numbers for the last outermost electrons in chlorine. So any of that five may have that. So one of the electron in that fifth will have a quantum number which is 3, 1, -1, 1/2, or it can be 3, 1, uh, -1, -1/2, It may be also 3, 1, 0, 1 half, or pwede rin 3, 1, 0, negative 1 half, and so on and so forth. That will also work for this one. We'll have there 3, positive 1, no. 3, 1, positive 1, either 1 half or negative 1 half. Either of those two. Okay, so we have there 6 possible arrangements, but any of that may be occupied by any electron. Okay, so in that, we may be talking about, we were talking about outermost shell. So we may be talking about what we call valence shells and NVE, or number of valence electrons. In that notion, the valence shell of chlorine is N3, right? And the valence shell of vanadium is 4. Why is that? So when we talk about valence shell, this is the outermost energy level occupied by electrons of an atom. Meaning to say, it is the highest energy level, where in that note, the highest energy level here is the 3. And for the vanadium, the highest energy level is 4. So for NBE, chlorine has an NVE of 7 and vanadium has an NVE of 2. Why is that? Looking into the valence shell, NVE, or number of valence electrons, is the number of electrons occupying the valence shell of an electron. So 7 electrons are located in the third energy level of chlorine, that is 3s and 3p. Why 7? Because we have here 2 plus 5. That's why it's 7. For vanadium, we have here 2 electrons for its valence shell, because we have here 2 for 4s. Okay? So in that, what is the valence shell and NBE of chromium, and what is the valence shell and NBE of argon? So this is the electron configuration of, or electronic configuration of chromium, and this is for argon. So if you are to look at chromium, the valence shell of chromium is 4, and the valence shell of argon is 3. Okay? NVE of chromium is 2, and the NVE of argon is 8. Why 8? Because we have here 3s, 3p, 2, 6. 2 plus 6 is 8. So these are the outermost subshell being filled with electrons of different elements in our periodic table of elements. You may look into that later on. So we have here the s orbitals. These are the alkali metals and the alkaline earth metals. We have here the transition metals, 3D. We have here the different boron groups, carbon groups, nitrogen groups, and fluorine group. Also, some of the noble gases. And here are some ground state electron configuration of different elements. These are actually shorthand electron configuration, wherein we use the electron configuration of the noble gases to indicate the electron configuration of different elements. And lastly, I have here an exercise. So for those who of you who will not be watching this video entirely, you will be missing this exercise. So for this exercise, this is actually a three-part exercise wherein for the first part, you need to write the electron configurations of the following. Do not use shorthand, please. Meaning to say, do not use the electron or the symbols of the noble gases. For part 2, write the shorthand electric configuration of the following atoms. In here, you will be using the noble gases. And for the last part, you need to find the maximum number of electrons that can have the given quantum numbers. So we have here, you're given here the different quantum numbers. Okay, so if you don't have any questions, okay, the submission bin of this exercise will be located or will be uh, available in our Edmodo group where you have conducted the exam. So I will be posting there as as I finish uploading this video. So the deadline will be on January 10, 2022 before 9 a.m. or before our class. Okay, so if you have questions, don't hesitate to contact me or contact Ma'am Gat so we can talk about your questions. Bye.